get to much like the second part. The transition from the first part to the second part of this course. There was some feature selection technique with basic one, and the question probably was for second assignment, except for the marginally fast time you have raised. You need more time, and just they can probably extend for 2 more days. And so go ahead and check out what function that is supposed to work is not going to work. Based on making the margin probit. See that really rather than you actually returning your assignment, you need more time and you can extend to a day because I was actually under the impression that since we don't have class next week, right? Constantly under the impression that okay, so we need to do some crash course on R for our intern. Turn out that we don't have class. All right, so today we're going to go through a really light topic. We're talking about linear statistical learning, and so the topic of the lesson. It's a broad topic, but actually very easy. Right, so as you know, the development of this particular scientific field, data science, some you may put it like data-driven statistics or something like that, is definitely highly influenced and challenged by the problem that we encounter from. For example, the data science is the most important one, and medical science, right? And even consumer statistics. And now with rapid growth of computer technology, enormous amount of data collected from a variety of scientific fields can lead to greater demand for those innovative statistics in the living method. In order to derive additional statistical inference from more complex data, for example, I just mentioned that consumer statistics, right? So those e-company, B2B companies like Amazon or Alibaba, they keep collecting user data, right? So now based on your browsing record or your purchasing record, now you have data, now they have data, they have your data. They can, for example, they know that at what interval, maybe a month or even a week or a couple of days, you're going to need this particular kind of grocery, right? You like almond milk, or you particularly found the ice cream, or your favorite clothes, the color clothes is red, right? So they can probably infer, right? So the most important part. Now we have a whole bunch of data, so what we want to do, because generally you cannot just do a cross tab or do a summary statistic. Okay, so I have 51% of my user are male, 49% are female. Of course, those internet companies, they don't need that kind of data. They actually want to predict your future behavior, right? Based on your past behavior, right? You know that you're going to need letters and letters, values, and characters, right? So you probably a fan of fruit smoothie, and they're going to know that. Okay, so for every 1 or 2 weeks, I can just simply display this kind of advertisement from your browsing environment, and okay, so it's time to purchase more lettuce from Amazon or other internet seller like food company, right? Or maybe we can, I guess the most widely used what they apply to is like recommendation engine, right? They can recommend the relevant website channel based on your past browsing report. Right, so you're a fan of, say, K-pop, and okay, so you like this center, you really like center belonging to center genre, right? So the process of, and that eventually led to greater demand for those innovative analytical methods to unpack those hidden information. And some of them were actually not clearly labeled, right? You need to establish this association. It's just there. And also, the other thing is that they actually do not have a clear textbook to tell you what to do, right? You would just, okay, so if it was average graduate, you know that, okay, so like a science graduate, an econ graduate, you know that, okay, whenever price goes up, demand should go down, right? Or you're a political science graduate, okay, democracy seems to be positively associated with economic development, right? But in this diverse field of data science, you do not have any prior knowledge of that. Sometimes you need to establish those associations. And you can only do that by exploiting those hidden information behind those data. So the process of extracting information with data may differ from that, especially from those unseen observations, so learning from data. Terms coined by some data scientists, and they use a very statistical technique that you have learned in past week or see in the future week. It's called statistical learning. Right. So it's usually applied. Right, so we usually use this technique to investigate those statistical regularity. For example, association is a kind of regularity. You know that whenever something increased by 1 unit and the outcome variable, or the variable that you assume to be the outcome variable, increase or decrease by a beta unit. And also, we also want to know, for example, say that, okay, so in the past, people simply do a cross tabulation. Say, all right, so based on this, we can generate this 2x2 table. Men are more likely to do that, less likely to do that, or a female is less likely to do that, more likely to do that, right? So we have this cross tabulation. Of course, the simple Ferguson distribution is now. So people demand more information that they can make future decisions. Right? Especially they actually want, okay, so people expect that, okay, so some prediction error may occur, right? That's probably what we have been doing in the past week. Particularly with respect to the error terms, standard error, our standard deviation. So they know that some prediction error might occur. Right? So they want you to make a decision with some quantifiable amount of uncertainty. Say with 95% confidence interval, 99% confidence interval. Right? And that decision, or say that statement that made with quantifiable amount of uncertainty, it's really based on this following clear. For example, you might say, okay, I've said, given, so this set of factors, this set of variables were percent, then the things, the outcome of each is going to happen with 95% confidence interval. And those variables that make this particular event more likely to happen is called the feature of the data. They represent for example, some underlying attribute or typical feature that they then more or less likely to occur. And the process is an estimation process of finding those features called feature engineering. So people are talking about feature engineering, how do we find an important feature of the outcome variable interest, and that's called a feature, right? The variable that has significance with respect to the variable. And we're actually more than that. For example, in the week I've talked about polynomial. We also want to know how each variable is related to the outcome variable interest. And this test is called functional form specification. So you may say, okay, so the variable, for example, x is basic form, is associated with the dependent variable function. But sometimes what exactly is quadratic form, second order form. The second degree form is more associated with the dependent variable because we assume there's a curvilinear relationship between x and y. Right? So if we want to know how the variable, by what functions the variable is related to the outcome variable, you can say polynomial or log function, right? So what's the purpose of that? Of course, gather all this information to help us make prediction on new data, because it's more like we care more about making a statement, not just about what happened in the past. That's pretty much like the fascination of social science. We try to explain, right? Whenever we do OLS, some people just look at R-squared. How much of the variance in y variable is explained by the variable, say x1, x2, that you put into the question. Right? But for practical purposes, right, we're going about how to make a statement, right? A statement in the past, about something in the past, happening in the past. We care more about making a statement about what's going to happen in the future, right? So that's why we need those information to help us make decisions. But there are the function formula that you're going to use, and the information that is useful for making prediction. And now your outcome variable of interest, for example. In machine learning, we have two types of learning. We have three types actually. Supervised, and reinforcement, and a bunch of other terms. But in terms of whether or not the given variable has a clear label, we have this following two main categories. For example, the first one, supervised learning. Whether we're dealing with continuous outcomes, so for example, there's a 1 unit increase in X variable leads to how many unit increase in kind of high growth, right? Or categorical means that they probably do not have inherent order, right? They do not rank, say chocolate flavor is higher than strawberry flavor because that decision, that preference differ from one person to another, right? Or polysynthesis, or this poly does not necessarily mean this nucleic acid will be superior to other problems. Or maybe a binary decision, either yes or no, so that was an issue more appropriate to deal with functional appropriate problems, right? Or unsupervised learning means that they do not have they actually do not have a clearly labeled outcome. That's how we usually do in text mining. We're trying to classify the content of the one task. So if they actually contain multiple topic, even though they may be weakly related. So, actually, some people actually like to turn statistical modeling as curve fitting, right? We simply fit this square curve, right? That minimize the distance, the square distance between each point to the average, to the average of your estimate, right? So suppose we have the following rule, following variable. We're trying to estimate, we're trying to find important predictor for the outcome called sales, right? And then we have the following variable, TV, radio, newspaper. So what we should do, we should put our AD or advertisement on this following demanding, right? A good predictor for this, the amount of sale that we're going to get for that particular period of time. So we can do that as regressive, right? Okay, so that makes sense, right? That seems that the relationship as established by previous research, right? So okay, so for say $100 amount that you put on TV advertising is going to lead to the beta 1 amount of increase in sale, right? But the problem is the biggest problem is to find a function that render the relationship to the outcome relationship. And this process called regression, right? That's what you say, regression. So we have this following form, right? All of them are plausible candidate for estimating the relationship between this variable and to the outcome variable set, right? But of course, that would require some hard judgment call, right? We all know that it's possible, so we definitely need For example, need some domain knowledge. For example, someone in the say school of communication, they will tell you, oh, radio is of no use nowadays because there's only a few people, maybe the old people still listening to radio. So you should not put your money on radio. So okay, so I get it. Or we can adjudicate the relative performance, say which specification works best. You translate the relationship of these two cells. So we need some other discrimination skills, right? Likely the ratio pass or other discrimination skills to guide our selection of model. So in general, the purpose of learning from data, so if you're probably laid out at the end of learning, right? Because we're trying to find out data distribution, how the data is distributed across the range of values, right? Instead, the data is right scale, left scale, because it's not a very well distributed, so we need to adjust their distribution or find out some variable, for example, come out of the Poisson regression to deal with that kind of distribution. And with that, we need to specify a function, appropriate function that uses as much information from the explain the variable interest to explain the outcome variable of interest. And then through that, we identify the relationship between x and y, and then we can use that to draw some inference. Then inference to make prediction, so that if similar kind of event from new data that we shuffle to you, you know that you probably know what to expect and what function and variable that you can use to predict similar kind of event if you can't find a new data. Right? For example, so here's some stylized example. So even from last year's data back, whenever temperature goes up, you should expect ice cream sale to also go up as well, right? And you find out, okay, so particularly for carrying and kind of the sales went up during the summer, last summer. And you find out that, okay, for those people who purchase this particular flavor, 65%, the great majority of them are male. So there's definitely some association there. Is that just male love this flavor because it tastes a little bit salty, right? You can caramel. Or it's probably in men's nature to acquire some salty taste, I don't know, to satisfy some their physical or human need, I'm not sure. Or maybe there's influence by some other personal feature that we haven't taken into account. For example, in a short article that I asked you to read about the pizza kit, right? Because of delivery in near the Washington D.C. area, but actually the particular article focusing exclusively on Pentagon, right? The Department of Defense or U.S. Department of Defense located. So you probably misnomer it because Pentagon is actually located in Washington D.C. It's in North Virginia. So they find out this particular association. Whenever there's a war decision coming out, for example, the president of the U.S. is preparing to make a decision to invade another country, right? You find out that, okay, so those meat flavored pizza, so meat lover, for example, the pizza having with meat, the salty meat, actually their sale actually went down. So people inside the Pentagon can order this kind of pizza. But they're making probably some peacekeeping decision or some military budget, right? So the amount of money they need to appropriate for next year's spending. There's usually some light flavor, maybe seafood or other vegan flavor. I'm not sure. So there's definitely some association. So you can probably use do some sort of data engineering there, right? To find out some feature that's highly associated with particular outcome variable. So okay, so whenever the flavor or the meat constitute a large portion of the ingredient, you find out that it's possibly associated with war decision, right? So you find out, okay, so that's probably related to something that's inside us. human genetic, I'm not so sure. So whenever you have this aggressiveness, and then you probably need to consume some salt to satisfy your basic human need or some inner drive. Also, we can also make similar statistical learning from longitudinal perspective. So from last week, we talked about the Smallwood Robinson's story, right? Said, okay, there's so based on their finding about the relation between economic inequality and democracy, we found out okay, in the past 200 years, there's indeed the inverse U-shaped relationship between inequality and democracy. So you might wonder that, okay, so since the world has changed, our economic structure also changed as well. So we have now moved from the agrarian society to a more, say, commercial society, and some people would say, for example, like the writer Thomas Piketty wrote the new capital. And they say that, okay, it's actually the financial capital that is currently dominating the whole world, right? There's an income distribution. So this relation is still hold? I mean, like for data like gathered after year 2000. So what can you do? How can you verify the accuracy of the theoretical model built by the Smallwood Robinson? Exactly, right? It's pretty much like what you would do with analyzing stock market trade. You simply use, say, you try to predict the movement of the stock market. So suppose this is where you stand, right? Stand at time t. Try to predict the movement of the stock market time t plus 1. Right? So you simply gather data. T minus 1, T minus 2. And use this as your training set, right? Does that make sense? And this would be your testing set. So you can use that to make a decision, right? So at this, you have 3 pairs of data, right? If you actually do more, say T minus T minus 10, you have to make a prediction on that. And then after the stock price is realized, say at T period, so basically you can evaluate your prediction for performance. Say if you actually guess the price right? So achieve that. So how do you achieve that? So we can actually achieve this by evaluating our model on some training data, right? Because we need to your model is built on some data, right? Constructed based on some data, right? But the validity of your model lies just on the data from which it's generated, but also on how good your model can be used to estimate the variation in the data, in a new data, or the data you haven't seen before. So the best way to do this is, of course, to first to test your model on so suppose you were given a set of data, right? So you want to generate a prediction model. So the best thing to do is, of course, to test the model that you constructed from the data on some subset of the data, and then validate its performance on the rest of the data, which you use as testing set. Well, because those two data come from the same data generating process, the topic I will turn in a couple minutes. The most important thing is that we want to make sure that the prediction the prediction that we made. So if that's a really good prediction, right? Regardless of the data that being given to us, the sign, say the beta coefficient, the magnitude, say the magnitude of the beta of the variable should remain mostly the same therefore it should be very local, right? Otherwise, probably not a very good prediction because suppose you got a beta estimated beta of like 10 in the first data set, but if you do the model, if you throw the model into say the R predict function and estimate out another data, you get a estimated beta of like 0.5. That means the variation is quite large. So your prediction, your predict model probably isn't very specific. Okay. Also, so on the set of variable that be significant in one model or in one data set, remains significant in other data sets. So for example, there are 4 variables that are significant in the first data set which were given to you. So you put your trend model on a new data set, but you find out that okay, only one is still there, still remains significant. So that means there's a change at all. So if they are now the case of what might cause this differences. So are you particularly simply from a really large sample? That could be the case, or simply your model specification is not very thoroughly considered. Right? Also, does a regression line fit the new data, or maybe the new data need to adjust your model using, say, the spline technique or our smoothing method, right, to improve the fit of your regression line to the data. Okay, and then lastly, does it still maintain acceptable level of accuracy, or maybe you have to degrade it as you move from one data set to another, right, be predicting the outcome of the data. So the most straightforward way, of course, is to validate the performance of your model on the same subset of data, right? Because it's assuming that okay, so if you're given the data, right, and then you should assume that they are all generated from the same data generating process. Especially for survey research, say, okay, so those survey responded. Okay, so the survey response were collected between between April to May, right? So they are pretty much collected within the same period of time, right? So you should assume that okay, so given the dominant trend or the dominant trend, even like climate, are pretty much the same at the time when the data are collected. So it's not subject to some exogenous shock, you economists like to talk about. So maybe if you collect the first batch of data today, maybe tomorrow there is some say economic crisis or simply the Russian president will be just launch a nuclear strike on say Ukraine, and then you find out people are getting panicked. So if you ask them to answer a question about their prediction for the world economy or about say defense, they probably get say more exaggerated response, right? So there's national defense definitely be important, and then we should hear about say the climate change because the nuclear fallout, right? So the data generating process contaminated by what's happening in the world. So the best things the best way to validate your model performance is to separate the data into investing in training model before the estimation, right? So that if you train a model, so you can estimate the subset of the data that's also generated from the same data generating process, so that they should probably process, so they are pretty much everywhere similar, right? So they should probably process similar properties, so that you can say with confidence that okay, so the model that I train on the subset of the data are still validated by another set of data which they haven't put into the estimation process. So you can make it say a conservative estimate. Say, okay, at this my model works well for the data that follow the same data generating process, so that I can have some confident about extending my model to new data set, which I haven't put it into my estimation process. But on the other hand, if the train model actually fit poorly on the testing set, say, okay, what actually the testing set is also gathered from the exact same data set, right? There was some random sample. But it turned out that okay, the model fit poorly in the testing set, even though they come from the same data set. Then you should probably go back and refit the model and increase the train test ratio. So that so if you increase the ratio of the training set, that means more information this particular data set is reviewed with your statistical estimation. So you should probably add more information regarding the variance, the distribution in your model, which should probably, not certainly, improve the accuracy in your model prediction, especially when you try to validate model performance on the testing set. And then check out the data. So in the third, we already processed that learning curve. And the important concept regarding the train test ratio and why you should do that is about data leakage. Right, so we know about data leakage. They probably heard that a lot. That's why people we reported cybersecurity consultancy or encouraging people that, okay, you should probably purchase the software that should help protect your company's data from data leakage to prevent identity theft. Right? That's fun. Of course, that's kind of like another way to look at the problem. But data leakage means that, okay, so because you want to use the model you train on training data to make prediction on future data. But before that, you want to validate model performance, right? Testing data that come out from the same data generating process as your training data. But if the particular feature that you want to learn are accidentally reviewed by the data that you put into your model, for example, if two variables are highly correlated, for example, if there's a variable in which you put as the right-hand side variable, as there is one variable, say x, is highly correlated to the degree of like 0.99. Highly correlated with your y variable, the outcome variable of interest that you try to predict. Right? So if you put it on on your training data, and then you use that to make prediction on, say, even your y variable, outcome variable of interest. You find out, okay, I got an accuracy rate is almost like 99.99. Does that mean that my model is really good? No. It's because it actually, say, put a variable that is supposed to be reviewed to your statistical model. So, for example, you could say that, okay, the model has good predictive power when it's predicting something that you already have some information with, then it's almost like an oxymoron. Because supposedly it goes all the way back to the basic OLS property. Like we try to exploit something with as few variables as possible, right? And also the variables shouldn't be correlated with each other. But somehow you do gather, say, a variable highly correlated with something you want to predict, or highly correlated with other, then but you still get good result. That means there's something wrong in your data, right? Because some information regarding the outcome variable interest has already been leaked through the variable that you include in the model, and your model can pick up this additional information so that it knows the underlying one, which is not good. Even though for some industry it may be good if you were trying to solve some question to try to crack others, say, cybersecurity firewall, it's probably good. But if you're just doing some statistical tests, that's probably not good. And how is code data leakage? Okay, so we definitely need this picture again in the future. But before that, we probably need to take a step back and then going back to some substantive topic. that will help us glean those key information about the data, especially regarding a situation in which the data being given to you, you have absolutely no information about, but you still try to gather or try to unpack some of the hidden relationship behind the data. Have you encountered this situation? Or maybe you have, say, doing some project job or doing intern with some data analysis company, or even just regular private company. Because I heard from my younger sisters, so those companies now have the position called BI, business analyst or business intelligence specialist. So basically, they just so those are kind of people that's supposed to know some stat, even though they may not, because she said the company actually tend to hire people who have absolutely no knowledge of statistics and just they come from a wide variety of fields. So the latest BI guy they got is actually from our chemistry engineering department. Who knows a little bit about Python, but is particularly good with SQL, to mean this data retrieval language, but don't know anything about stat. It was really amazing. And then you usually throw in her a bunch of data from OS battle live, and then you ask that person to give you some, to tell you something about the data. So for example, this could be you. So your client give you a bunch of data. They contain millions of observations. Right? So you try to redirect you to think about this question in terms of like data structure. The number of observation is the row, right? Row vector in your data frame, right? Number of row, right? So you should always say, whenever you download the data, you should not just, so you can, of course, it's a good habit to, to assign the data you just downloaded or you just record, be given to as you should probably assign a name, right? Say DF or DF1 or my DF, my data frame, right? But it's not advisable to simply type this name on your R Python screen because it will list out all the information. But you do not know the size of the data, right? If you have billions of data, then you'll find out that your computer will crash. Right? So it's always advisable to simply do the data or dimension check about how large the data is. But suppose your client gives you data that contains billions of information and hundreds of variables, and those other variables are transformed in various forms. See that? Okay, so we have temperature squared. What is that? Right? Temperature squared. Right? And some binary information, some just text, a text string. Right? You cannot use factor text variable, an untransformed factor variable to run a regression, right? You need to transform it into something else. Or you give it a label, give each of that label. Right? And your client, being the mostly he or she asks you to present preliminary finding next morning, right? Otherwise, it'll take my business to someone else, right? And then you lost your job, right? So what would you do? Meditate. Trying to figure out what to do, or just do what you're going to be trained to do. Number crunching, right? Do data mining, right? Pull out lots of correlation table, given that the data frame has millions of observations, hundreds of variables. So there are lots of cross calculation that you would need to do, or apply. Low-E sluicing or log transform on each and every one of the variable, right? Trying to find out if they're actually something that's correlated, right? Because back in the old days, I got refunded something. Professor actually asked their research assistant to do this. They actually did not know any information regarding data frames. So just test each pair of the data, right? And we were talking about if we can actually write a paper around this, actually don't have any idea about data. And you should probably use your visualization skill to do some plot on this, right? Trying to figure out at what particular range of data this, so there's a pig, right? Or maybe there's a thing in the bilateral relationship. And then it might be something interesting even though you don't know anything about it. Or you can ask an oracle. So what is an oracle? Anyone know this person was seen? Anyone watch the Matrix movie? Played by Keanu Reeves. It's almost like it's two decades ago. I think this already appeared in the second sequel. Right, so yeah. Actually quite ahead of time, so we can spend some time about that. Before I do that, so anyone give me a definition. What is an oracle?
I'm sorry.
It's really going to phase you a little later on is we just didn't grow up. I can see why she likes.
Right? Yeah. Anyone want to give me a working definition about what an oracle is?
I can see the future, predict the future.
Because,
Yeah.
I mean, the ability to see and tell you someone about what's going to happen is because the oracle already know the truth, right? Right? That define the oracle means that, okay, so he or she already know the truth, already know what's going to happen, so that he or she can tell you what's going to happen. That's the oracle. So in statistical estimation, we definitely want a technique or some method that can tell us about the underlying relationship or structure of the data, right? Especially when we know nothing about data and we don't have time to study the data. First of all, you come from the discipline of the chemistry engineering, like you hire from the system, chemistry engineering. And he doesn't know anything about economic political science, but he's just being given the data about something about what's happening in the world, about to study the relationship between GDP and level of democracy, probability of war between countries, right? So it would be better if teacher rely on some technique that would tell him, all right, so what variables actually are related and how are they related, the function for specification. And if I'm going to make prediction model, so you just write down my prediction, my model specification, right? Because in order to write a valid or model specification, say the x, y, that makes sense, right? You need to have some domain knowledge, right? I mean, at this, you should have some intuitive sense about about what kind of variable should be related to what, right? And how they are related. Say democracy, right? Economic development. Say, okay, so probably some positive relationship. And so the probability of war, there's probably some negative relationship because war, militarized conflict destroy everything, so the country's going to have low economic development. So you should have some basic things, but sometimes we just get too busy, especially whenever you're being thrown with a data set that did billions of observations and hundreds of variables, and you have absolutely no interest to know anything about, right? But you're forced to write down the statistical model that makes sense, right? So lemon needs and technique ever tell you, right? Here's a list of candidates. K is a K variable. They are important predictors that explain major variation in the outcome variable interest. And even better if the model can tell you, right? For the first variable is significant with the dependent variable interest at its basic form. While the second variable is significant with the dependent variable via the log linear transform function. The third variable isn't significant with the outcome variable interest, but it's significant at the second degree. Right. So essentially that kind of technique would make a recommendation to you. So all right, then here's a potential candidate, a variable that serves as important exploitative variable for the outcome verification. And this is how they are related. Right. So it would be best if we have a similar tool that would guide us to make a decision about how to do model specification. Right. So here's one of them. There's called a least absolute shrinkage selection operator called LASSO. So it's a regression method that performs both variable selection and regularization method to enhance prediction accuracy. So we're going to come to this. But before that, I ask you, so how do we evaluate prediction accuracy? That means we have smaller error, right? So they should definitely capture something that can help us minimize, or something reduce, which is minimize, and that's probably way too many. There's some square error, right? Here we have smaller error, that means our predicted value from the set of variable is close to the true value here.
And
to the ability to interpret statistical model which this model application will produce. So the first part is selection. So only variable that have improved prediction accuracy will be selected, meaning that they have strong relationship with the outcome variable of our interest. The second part is called regularization. Even though there may be some rather abstract to understand at the moment, but you should probably find out why later. Because this is achieved by adding a penalty term that equal the absolute value, that is for the LASSO model, equal the absolute value of estimated coefficient based on whether the variable, so that's the estimated coefficient of the variable, whether that variable, so you should know that this is the big answer, right? Contribute information that minimize some square error, right? That improve prediction accuracy by reducing some square error. Otherwise, the estimated coefficient should be shrink to 0 because they will be kicked out from this process. And throughout this whole process, the two-stage process, then we should probably only be left with few variables that remain, then that should be, so they should, so they're equivalent to important feature of the model, because the reason that is still being left out is because they retain some strong relationship with outcome variable features. So the second step essentially is this feature select. This select important feature of the data set that are strongly related to the outcome variable features. All right, so we take 10 minutes break. Right, so for the lasso function, you know, like, okay, so I already know this part, right? Sum squared error, right? So larger sum squared error means that there's more prediction error, right? There's a larger deviation from the predicted value of X times data, right? So there's a larger squared error between the actual value and the predicted value. So this part is entirely new, right? We did not know anything about this. Right. So that means, okay, so for the total of 10 observation, and after working through this process, we will only have J of all the variables, of the P variable will be retained. Right? So how does that achieve? And what is this? Right, so before you look down the bottom line, we need to problem page. So that's that. Okay, so they actually use this part to do some constraint optimization, or minimization problem. Meaning that, okay, so the best from what we have learned in the past week, the blue model, like the best leading unbiased estimated model, is something that minimizes, right? That's why we should apply this square regression. That minimize this part, right? So that we project hyperplane to a multi-dimensional space that minimize all the square distance between each point and this square point that we just projected, right? That's pretty much the summary model. What we'll be discussing in the first couple of weeks. So that's the first part. But here is additional requirement. He said, okay, so for those variables that did not contribute any information toward minimizing the sum square error, meaning that, okay, so if you have a variable that has small beta, right, then we will assume that this part is square distance would be will be very large. Okay? So make sure that it was on the same page. Right? Okay. That kind of variable means that variable x with small beta, small coefficient, will be relegated here. They will be penalized. Right? And the amount of penalty is determined by the lambda. That's the penalization factor in the decimal model. So they were penalized by the second term. So this is how it is. So if we have smaller, say usually the lambda value is smaller than 1, meaning that we have smaller penalty. So there are, so if they have lots of variable, then many variables, even though they might not have a strong relationship with a given variable, they were still remain. They were still there. But if you say we want more aggressively penalize those variables that did not contribute any information to minimize the sum square error, so we simply increase lambda, the magnitude of lambda, right? So that more variable, so if they would not have beta value, they would be relegated to this part and certain region. So they will be kicked out if we increase the size of lambda. So that's the penalization factor. So smaller the lambda, smaller penalty, you want to accelerate penalty to pick up more variable or important variable, we just increase the lambda. So because of that, there's a broad class of penalty function at equal codes. Is it a group lasso or explicit clip, absolute deviation for scale, which we're going to use in the data part of this lecture. For the minimized contained penalty, this is something called adaptive lasso. Right. So here's another related model that's almost similar in every way, except for how they specify the penalty. So you know I found the lasso, the original lasso model. This is where you're gonna this absolute value, right? Or the beta term of the ghost variable that has smaller beta coefficient. They contribute a little information to minimizing square error, your model square error, right? I mean, the beta term can be think of as the effect. Even though they say nothing about significance, I'll make sure that we have a same data because I'm not going to go to the class saying, well, so how do we deal with standard error? No, actually, we look at standard error. So, okay. That means because beta is usually interpreted as, say, the slope of the regression model, right? So if you have a rather flat slope, meaning that okay, so the variable probably has nothing to do with the outcome variable of interest. So it did not pick up any information. If you include this model as a predictor in your regression model, and you have like the beta value almost close to zero, meaning that it did not pick up any variation in the variable. So that means the x variable that you use as if you respond to the variable probably have little relationship with the outcome variable of interest, right? So that you just relegate it to the penalty term, so it will be kicked out. But here, there's another related model for ridge regression. Use the square magnitude of beta as its penalty terms, is the specification for the penalty term. So this is what we call L2 regularization. So as you probably know, what's the consequence of that? Right? We use square term, meaning that okay, so the small differences will be magnified, right? If your predicted value differ from the actual value from by 2 units, then you square that, the difference is 4 units, right? If your predicted value differ from the actual value only by 1 unit, you square that to 1, right? So they kind of magnify differences, right? But if the difference is really small, say on 1, then you square that as 0.01, so it's smaller, right? So it's also carried some shortcoming, of course. But there's one thing that they have in common. So if everything here is just zeros and the penalty here is just zero, so they are pretty much they're just the same thing. They're just the ordinary least square regression, right? So if then that zero, means that the model did not penalize those variables that contribute little information toward minimizing square error, then the model just comes down to ordinary least square regression, right? And of course, there's no penalization mechanism occurs, so only very few variables for no zero entry or also very few zero, so the output is So if you increase the size of the lambda, meaning that you can increase penalty, so there will be only just a few variable left. With non-zero entry, so there will be hit in the model. Well, most variable will restrict to zero, so the output of that is expected to be very smart. It's exactly what we wanted to do, right? Especially being given data set that have hundreds of variables. Right? You only want to keep only a few variables that can serve as according explanatory variable to the dependent variable. Right? So the output we left out usually very sparse. So the output of that model will be very sparse. So it's well suited. You kind of this property make it decimal well suited for feature selection, but because we use absolute value, right, for the same data. So the coefficient estimate can have multiple solutions. So that can be less stable. But when but also for okay, so I forgot to add this. The method that used the absolute value is called the L1 radicalization. So of course we have L2, meaning that we use the square magnitude of the as a specification for the field feature. That's for L2. But we also carry some that property. It's whenever, or because since you use square magnitude, so it's very sensitive to outlier or to the small fluctuation in the difference between the actual value and predicted value. So if a lambda is very large, then you will add too much weight, right? And eventually you will get to underfit it. But you kind of pick out a small fluctuation, small variation in your data, right? So it could be into underfit. But however, a unique solution for beta can be identified by this technical process. To skip this part. So we can identify some unique value for beta on L1 radicalization. So previous research has shown that L2 cannot shrink the coefficient and correlated predictor to each other. While L1 just take one of them, take out the other. It's like, okay, so since both of them carry some good things and bad things, so can we do those? Yes. And there's a middle ground, elastic band. You can preserve the property of those last sum and reach regression, and essentially just connect your gapping function through a term called alpha. So you should know that. So if alpha equals 0, that means L1 will be good, right? L1 relationship will be good. Well, L2, since 1 minus alpha equals 1, means 0. L2 will get out. So if you do this one, do elastic math by setting alpha equals 0, possibly that value is just less of regression, right? But on the other extreme, if you set alpha to 0, it means that this one will be right. And so L2 is retained. So if you set alpha equal 1, alpha equals 0, then it is reduced to reach regression. So it's very flexible, right? You just simply adjust the alpha, depending on how much weight you want to put on the penalization mechanism of the lesser regression or the reach regression. So you kind of like try to get the best of those. So the tuning parameter is still the same. Again, the lambda still control over less of the penalty. So we're going to do some exercises. Right, so here's our workforce package for this exercise. We're going to need GOM AT, GOM NAT. Also, we need a more flexible trend function from the Correct package by Trin Johnson, and so we load those packages. So here's the data set that's compiled by yours truly, me. Right, so the data set I used to write my dissertation. So it's called the CBI as abbreviation for Central Bank Independence, right? So here's the backstory. Back in the 1980s, we started assuming that, okay, so in order to stabilize the economy, to make the policy announcement of monetary uncertainty more credible in the eyes of the private investor, otherwise the country could capital flight because politicians aren't really trustworthy, right? So we should grant our central bank a monetary authority or autonomy. So that's why we call for central bank independence. And the argument is, so only democratic government are willing to grant a central bank independence. While for more authoritarian government, they probably try to maintain the policy, they have the leeway for making those flexible policy response to outside situation. So that's the basic argument, and there's a bunch of scholars. Kukiman actually they compile some central bank independence index. Higher values associated with greater central bank independence, lower value, lower autonomy. Right? So here, I mean, that's the best way you don't need to really that's the way we are supposed to have we don't know anything about data. But here's the backstory anyway. So here's how you can download the data that's stored in CSV format from internal source. So if you download from external source, you should probably be closed out with the URL environment. For example, you download from other people's archive, which you should store the data from the web accessible location, and you should call that read data format URL, and then your link. So R would be, okay, so that should be something that can be connected to web, so or download data from here. And the data must be stored in, say, since I use CSV here, most possible, the data could also be stored in, say, data format, that would be DTA. That's how you download them. From other source, but here, since I have the Dropbox folder, only asset folder B, so this is external data source. But of course, but since I found that for actually many web applications, you do not need to enclose that with URL. But in case that for third, you should try to enclose it with URL. But here it doesn't need. Right. So the second says that we set that our required variable. We only need those variables, so we only work on the column vector. Right? We can also rename the variable. So there are times when you find that, okay, so the data that you're working on, the data name is not very intuitive. So maybe data name is just too long, then you might want to rename it. So the best way to do so is simply apply a name function, so it will list the name of all the variables inside this data frame. And then you can set an indicator to leave that, so saying that, okay, I want to rename the first data name, CBI, but the CBI could give me as too long. Force, GDP, right? Fifths, financial limits. And then some of you have encountered for our second assignment about making a quadratic variable. There are a couple ways to do that, as I said. If you want to work this out inside the LN or GLN function, or pretty much all the regression functions are, you should say LN, for example. It's plus. If you do not want to alter or append new variable that you generated outside of the data frame. So you just want to keep one variable. You don't want to contaminate your existing data frame. You can open up the indicator function, right? I raised to the second power. So you serve as a calculator, right? You open an environment inside the LN environment. So you can have the direct calculation inside the LN environment. You just do the same for so on and so forth. But here, just here, so for example, I want to append a new variable generated this way. Right? You can also subset the particular variable that you want to transform and from existing data frame and create a new variable out of it, and append it under existing data set. Even though it's not recommended because you can contaminate your existing data set. You can get really messy, and at the end of the day, you actually forget. Let's say, so I forget what's the purpose of doing that. I have no idea why I created that variable in the first place, right? So you can also use log inside it. Same for if you want to do this inside a model algorithm, use log inside it. Right, so now you can rename it, so I could create two new variables and append it into underlying existing data. Another way to do about subset of data is to get observation that do not have missing value in any of the columns. So we can do that with the complete case system, right? So you close namely your data frame. So you will retain those observations that have complete that do not have NA value, missing value on every column, every variable. So only when you have full observation will be retained. So if you type you find out that number of rows reduce significantly. Well, suppose your data had lots of missing value. Check this out. We find out. Okay, so there are two more variables being appended to the existing data set. And then the good thing is the reason why I want to use the carrier function instead of the GeoNAND is because, okay, so I'll show you how we can set our own control function. Even though I haven't taught you the cross-validation here, it will come to you in a couple of weeks, but here it's just almost like a shuffling. You randomly use 1/5 of the data as your training set, and evaluate your performance on the. No. So actually use 4/5 of the data as the training set, and validate it on 1/5, the rest of 1/5 of data. Right. But you do this 5 times. You go cross-validation. So for example, so you're given a data set, and we randomly cut it into 5 parts, right? So for the first iteration, we will use the first 4, and so it's 4/5 of the data as the training set. And then use the train model to predict the 1/5 of the data. Right? And for the second round, we use the other, or 4/5 of the data as the training set. And you use the train model to predict the other 1/5 of the data, 10%. But iterate 5 times until the only iteration I use. So it's called cross-validation. Again, for reproducibility, we set C to, you can set the set to pretty much everything. It doesn't matter. It's just someone want to look at the exact result generated from your code. And then we can first get a rich regression. Okay? So here we specify our trend control function as a 5 times cross-validation. So we name it as control. We'll put it on the trend control function, right? It's just the step that we just specified. It didn't come out of nowhere. You also notice that, okay, so the data argument, I know that message of GeoNAND is probably going to do the elastic now. But you also know that the preprocessing argument is set up center and scale. This is because this type of model is really sensitive, as I said, especially for rich regression. It's very sensitive to outlier because you need square magnitude in the speed of the term, right? So it's better to standardize it, right, before applying a rich regression. So you should center and scale. And then we say that alpha and beta, and you should note this here. So what do I set alpha to 0? because we're doing rich regression, you just set alpha this guy. You set alpha to 0 as far as out, right? So you're left with rich regression. So on the other hand, if I'm going to do lasso regression, what should I set an alpha? On the y part, right? So, all right, so we fit this model, and then so before I did a summary to look at the result, you should probably extend back, look at what's inside of the result, right? What's inside this trend object. So, well, there's a lot of things, right? The tell you the information, where the preprocessing step, which you have just did. So one thing to look at is simply to the coefficient, and then we just select the final model, and then look at the best tune lambda, meaning that the value at which the lambda is optimized, because there is a bunch of lambda values. Okay, so we can actually look at their beta coefficient. And we can do the same with lasso regression with the same tree control function, but here we set alpha to 1, right? So that the L2 regularization is being taken out. And we only then use L1 regularization, which is lasso. Right. We can do the same thing to look at the result. It should be a little bit different. I mean, a little bit different, not differ very much. So that's one way to do the lasso enriched regression. But of course, you should probably know that the author, if you want to do this in the trend function, as written by Kuhn and Joseph, the author of another of our textbook, right? So that we specify the method of GOM now. Right? That means that they're actually taken the R code from Ficciarani and his co-author. Right? So essentially, the algorithm working on that is the same. Right? The author of the trend function just taken the GOM now code, right? Taken the Ficciarani and his co-author's code to use on their trend function. So you say, okay, I don't like the trend function. I'm not jealous of this possibility to do this trend iteration, cross validation. I just want to use the trend function. Of course, you can do it. So you just use the GOM map. It's a slightly different because the author, as we introduced in our lecture, said because the output lasso regression is generally very sparse because as you increase the magnitude of lambda, the penalization parameter, so there will only be a few variables that we left out. Right? So the output is a very sparse matrix. So in author, I will highlight this. So it says so for the object that should be fit into the GOM map, it should be converted to a model matrix. So we need to apply model matrix argument by first specifying the formula. So we simply regress the CBI. So use the CBI as a subset data, CBI sub. Use CBI as our even variable, regress on all the variable except for the constant term, the interceptor. So here with -1. So you will create a matrix that whose number of columns correspond to the number of variables that you put in the model. So essentially will become a very sparse matrix after this matrix. Again, we should specify a y. We can just simply subset it from our data set and y just to see the even variable. And now we have our x and y, right? So just put it into the GOM net function. Since we are doing rich regression, so we set alpha to 0. So now we have the output. And the bad thing is that some people just, okay, so just apply summary and apply summary function on this rich regression. No, you cannot do that because you apply, you have to play this on your R or RStudio console. If you do that, it would just give you a summary of the description of the class of the model or the candidate side of this model. So you should use, say, the print function to see see that. Right, this rebel line. But the pre-function will only show you, say, the change. Also, it's also the change in lambda. The lambda value goes from lower value to higher value. So the effective degree of freedom in a variable is still being left out in the model. In order to view, say, the stuff that we really care about, beta coefficient, again, you need to apply the same thing. Should apply the coefficient function, and the first argument should be your fitted model object, fitted GON and model object. This can be confusing for someone because student is saying, so what is this? I didn't see that in our lecture notes. If you look at the authors, I think that they have a web page. They said they use S to denote lambdas because they try to preserve lambda for some emails. For reason I don't know, because I didn't write a GeoM code. So if you have a problem, say I force the demand that you should have lambda, you should write in the email. I can see. So you can use this function to check. So S means lambda, so we'll emphasize this. So this will tell you this many coefficient of your estimated GON and model could be doing ridge regression. Optimized at the best, and this is the first one. What is this? Well, actually, I did not create it. It's that we found your modeling option. So if you type names and the output, you see this. So that's the optimized lambda, at which the value, the objective function is optimized. So of course, we want to plot it, right? So we can simply apply plot, use estimated GIA and object, but it doesn't look pretty, right? So the recommended method, of course, is to use plot mode function. So we simply download the package and load the package. So here's one simple plotting command. So car, now the name throw means a multiple row. We call it as well. So that means, since I set out 1, 2, so the 1 is my row vector second, and the 2 is my column vector. So I want to, so if you, so for example, sort of like when you're writing a homework, or it's just I didn't ask you to do that, but you can just do that, especially if you want to do more statically placing output. So I want to place, say, 2 figures side by side. So that means, okay, so you have 2 figures, and then you want to play that single row side by side. That means you want to set out a plotting environment before you do the plotting function. You say, okay, 1 by 2 means that 1 row, right, 2 columns. So we want to set out, say, we want to perfectly arrange 6 blocks by, say, 2 rows and 3 columns. So that's going to be 2, 3, right? That's what it is. And then we can call the plot GeoM function from the plot mode package. So basically put your GeoM object here. Specify the X variable and so the number of variables that you want to show the label with. So usually they are the top nth variable that the model will pick as being important explanatory variable to the outcome derivation. Then you can use an expression from it as so here just supply the code for you, but you want to get more complex. So is it possible that I could do some Greek and Latin lettering and also including subset and subscript and superscript, like just email me because that should be relegated to other subjects beyond discourse. regular expression, right? And then do your y lab, so beta. So what does this graph mean? Right? But the plotting command just materially, but what does that mean? Okay, that means, right, so on the bottom x-axis, that means that's the scale of your lambda penalization factor, right? And we know that before looking at the graph. As the magnitude of penalty increase, the variable that will remain should, the number of variables that will remain in the regression should decrease, right? Because of the penalty term. And the degree of freedom is the effective degree of freedom means that the number of variables that are still in the model. Right, the beta is how do we interpret the beta? Also, you can see the labeling for it by color, usually variables to remain. Beta means that, okay, at this magnitude of lambda penalization factor, the beta is the estimated coefficient of the variable. So you can see that as the magnitude of penalization factor increase, almost, I should say almost, is that all variables, the estimated coefficient of all variables shrink to almost zero as penalization factor approach to this one. That's the next gap. So, any takeaway from this graph? Also, so you say, okay, so I want to look at the coefficient estimate, evaluate a particular lambda penalization factor. You say, okay, so I supply the 0.1. You can do 0.2, 0.3, or like 50, 0.3 value. So you could do simply the cross-value version of GOA in there. So you just say, okay, so do reach regression, then you set alpha to 0, and then your value is right. And you can also look at, say, to look at the result at lowest lambda, optimized lambda, and we will show you that. And also you can look at the result, for example, is my coefficient at when lambda is evaluated as greatest value, so that should be lambda 0.1 is the largest lambda inside your model, so they will display the coefficient estimate. But so far, you should probably look at, so you can probably get this question in your mind, say, where's the standard error? The most important thing is standard error. Suppose you are a person like me, say, whatever model you're doing, even for the Bayesian model that which we shouldn't care about, estimate the standard error. We will simply use the upper and lower bound. Because for p-tracer like you, always care about the p-value. You want to know whether the variable is significant or not. So where is this standard error? Right? We need standard error to calculate the t-value and also infer the p-value. Well, actually, for this application, they don't have it. But if you really want to calculate, you can also use simulation method. If you really want to calculate that, you can only do that with some bootstrapping, simulated error, or to calculate it numerically by the upper and lower bound. So 2.5%. So lower bound is 97.5%. The upper bound is calculated. So you can use that to subtract on your estimated value to get a standard error. But those are not the real standard error. So at below, actually provide you with the code to calculate the bootstrap standard error, which I would now explain it here. Right? All right, so last part of this lecture. Right, so we know that, right, so they have this really good property that also serve as a useful tool for us to do feature selection, especially on data whose distribution we know very little about. Right, So, what values we have had. Now, especially regarding the function form specification, so how is the variable related to the outcome variable of interest? Is that through the log transform version, or as second and third degree polynomial, or maybe it's interaction term, right? So you have talked about the potential nonlinearity within the interaction term. Right. So maybe the relationship between x and y is moderated by some other variable called z, right? So that could be really hard. Still, if we want our reading, I could pick that reading because it doesn't particularly hard. It's very easy to read. So we propose method of adaptive method that use scales, mostly absolute deviation, which I just showed you a couple slides ago. Show that there's a rational model you can have oracle. That's why the oracle comes in. It performed well. It tells us what variable are important exposure variable to the outcome variable of our interest, and their function form specification, I mean by the way through which is related to the outcome variable of interest. So almost as good as you actually know the true underlying model. So that's where it comes in. Does anyone know what Wonder Woman is talking about? What is it so movie? No? Actually trying to use this graph to help you memorize this fact. No? Would you like to Google this one? Type Wonder Woman lesson. What would you get? One. Because I was under the impression that it seemed like to do it for answer, but it didn't turn out that way. That's not the lasso of truth. You can use that to ridicle someone, and he or she will tell you the truth. So the property of this lasso function, meaning that kind of like the protagonist of the topic of today's lecture is that, so in word, as if he knows the truth, and if you apply it properly, you will tell you the truth of the underlying statistical property of the data you are working on. So here is our last exercise. We apply the polywalk package. Another say English vocabulary test. So what is a polywalk? Well, it's not pronounced this way. Where it's not pronounced this way. It's just a variant. We type polywalk and frog all the time. It's just frog is infant form. So actually, I was being told this story by the programmer of the polywalk package to say, okay, so his advisor tell him that, okay, so to write a statistical package that will have high impact and that's almost will be remembered by everyone is to have a cute name. So that's why it's named as a polywalk. So so he basically used the state version of the lasso, the adaptive lasso, but it's very flexible in terms that you were to take all the variables that they put into the model, and then randomly, so we'll generate some, we'll generate all possible combination of this term. For example, it's polynomial term, and you can also do log transform, okay? And also interaction term. So if you put the three variable into the model, it's x1, x2, x3. So you will include their basic form, okay? So then their interaction back. 3, x1 x2, big 3, and x2, 3, and they're higher order form, depending on how you specify the degree. For second degree polynomial, then we have, right? It will also include polynomial version of interaction of, say, x2, 1, x2, right? So this is a really lots of term. But because we know that it's based on sparsity of the last regression, only a few of them will remain significant after you do the analysis. So that's why it said that this function is best used for, especially for data that that have lots of say lots of variable, and for most of them you have no interest in knowing. So you can help us. You facilitate your handling of those data, even if you are a mindless data scientist. Right. So still, we're going to use the CDI data and then do that. We're just doing this for demonstration. So we call the library, and we fit, right? We don't specify anything. We just regress out all the variable, including the constant term. And we set the degree polynomial to second degree polynomial, really set a threshold value, it doesn't matter. And then we have this, we summarize the data. You should also know that it doesn't come with standard error. We can get that later with the appended bootstrap function, generate bootstrap standard error. And we can plot it. But before we go down the plot, we can probably look at it. Okay. So okay, we have the original qualities to just a level democracy quality score data set. Level inequality for Gini coefficient. The quality square that was specified second degree polynomial. Right? That's how their interaction term and inequality square. Right? So we just specify this that you're already down a lot of those. So we can plot it. So what does that tell us? So okay. So even for someone who doesn't know anything about the relationship between democracy, inequality, and central bank independence, you know that okay, it seems that inequality has some curvilinear relationship with our dependent variable, central bank independence. Right? Instead of resemble something that you already read on that's probably wrong. I don't know, but I mean it's just this the purpose of doing that is just assuming that you're mindless about the data, you have no idea what the data is. Right? And then you say, okay, I feel very uneasy for an output that doesn't come with standard error. Okay, so you can do that with bootstrap function. You apply the foo polygon and say 5-0 bootstrap. Or five times bootstrap application. And you will estimate simulate standard error for you, but it's not a real value. Just give you some simulated standard error. You can also do cross-validate it to improve the validity of the model, the consistency. You say, okay, so I want to evaluate and cross-validate it 3 times, right? 3 degree cross-validation, 1 to 3. This means 1 to 3. A 10-fold cross-validation. That means we randomly use 9/10 of the sample as our tested as our training set, and then use the train and apply a train model to pass out the remaining 1/10. And we do this in for each across each iteration. So here we got it. So before that, you can also look at what's inside the feedback. So it has a name and lots of that. So if you really want to look at the result, you should just go and use the summary function and to subset to retrieve the polygon fit, the fitted value inside this. You see that it didn't have that. Right? say, okay, well, I have the estimated available coefficient, but it doesn't come with standard error. To get standard error, again, you need the bootstrap to get standard error. You can also plot the marginal effect, but here, I think he probably grabbed the marginal effect function somewhere. Again, you just apply this on your estimated, the fit value that you were plotting. Again, it still shows that inequality has the curvilinear relationship with another thing that I want to show you before I let you go is that, okay, so we have gone through the first part of this. Right. So you can, when you get home, you can probably look at this as a refresher course, or simply doing this as a review about that. Right. But here, because I was saying that the central independence data I use isn't very ideal for feature engineering test. You don't have two field variables, so the number of observations is like 2,000 something. Right. In order to show you how relatively buffer tools, so here we apply this on the more demanding data. So I have this like credit card, credit fraud data set. So actually, the original data contained over 1 million observations. So since I already pre-processed this, so you shouldn't have problem loading that. So you can download it from this from our shared Dropbox folder, or pretty much anyone with this button. So I simply subset the data, right? So I rename the first column, right? And then I compile. Pretty much the for observation is card handle value equals 1. I will subset those data. So we got a smaller subset of data and rename it as data frame. For the easy type users, I do not need to type that a lot. Okay. Again, I also retrieve those complete value and I set red and C to do trend test split. So here, because I have larger data sets, so I can squatter away. So I can have lower, say, trend test ratio. So I just do the 50-50 split. And I use that you already know, the trend test split. And then I have my training data and testing data. So I first apply the lasso regression for using code that you should already know. Right? So I listed this the estimated coefficient and the largest lambda value you may cross-validate from GLM and the lasso regression. You find out, okay, so almost most variables just disappear, right? It's only like 2 variables left. There's income and not spending negatively associated with the outcome variable. I can also do receiver operating characteristic tests. It's pretty much like numerical value is an indicator for the accuracy of my model prediction. But we'll definitely come to that topic later. Good measure to go back to the RC, you see that. We can also do ridge regression. So again, we set alpha to 0 if we get ridge regression application, then we can do that. Okay, so it seems that the lasso model is more revealing for the data set at hand, because if we do the ridge regressions, then almost all variables still there. It doesn't do that much feature selection. It is according to this our model specification. We have a calculator receiver algorithm. And finally, so our final version is on the estimate, because assuming that the estimate used the alpha parameter to adjust whether you should get L1 regularization more weight or the L2 regularization more weight, or maybe something in between, right? So we apply estimate. Since you use both regularization method, and given that the data contain over 1 million observation. So it's assuming that it could be more computationally intensive. So what do I do? So how to make the best out of your computer? We can do some parallel programming. So this can be done by first using the following argument to ask R to detect how many cores your computer is running. I think nowadays that you would kind of like the basic setup is like 4 cores. But likely in last year, the students only had 2 cores. So I said, oh, then you should probably go for this. Should go for this part, because if I apply this one, then the computer would just run on 1 core. It's not much different. So, can you tell me, so what's the reason that I just deduct 1 when your current, your total number of cores in your computer? Probably just lay out the explanation. Well, it's because we did not know the size of the data. Well, of course, here you already know, because I already tell you right, the lesson, right? I already tell you, right? It's over 1 million observations. Well, of course, if you're expecting that you're downloading billions of observations, so what's the big chunk of data, then your computer probably crashed, right? Including the things you're working on. So you're chatting with your friend, you're working on something really important that you'll be turning tomorrow. Then your computer just crashed and you forgot to save your current memory. Then that would be bad, right? So you say, okay, I will leave 1 as spare for my current working environment. I'll allocate the rest of my core to processes instead. And then see that then you close inside the main cluster B allocated. I will register this cluster. It's a number of cores. If you type this, it will show you the current the number of cores in your computer. So the total number of cores in your computer should be this value plus 1. So I'm sure expect to see maybe 4 or 8. So the current Mac will should be 8 cores. Yes. And then you register this core. It's a do parallel function. Previously, we actually call a package called do part. That's the parallel computing command. Okay. So R, the current operating environment will enter that. Okay, so I will distribute those data flow equally to those cores, to the total number. And then you specify the alpha. Right? So you would run from 0.2, meaning that, okay, so lower alpha means that we allocate lower weight to L1 realization, or higher alpha means that we allocate lower weight to L1 realization. But on the contrary, similarly, you can say lower alpha means we allocate more weight to L2 realization. Higher alpha means we allocate lower weight to L2 realization. So we were incremented this by an increment of 0.02. So here is just write a for loop. So it's to iterate over this range of values. So I equal alpha. So iterate first the range of value by increment of 0.05. Right. So using the do part command, we put in this argument here. So we're varied by the number of alpha. And we say parallel true. So because nowadays it seems that many are programming expecting to do this, so we tend to include the parallel command. I think that like on the network model working on the Ergun initial random graph, they also have this parallel command. So you actually it's very convenient. You guys don't need to do this about it. Just say parallel true, and they will allocate those information flow to the core in your computer. So we do tensor cross validation. And we want to come back and calculate the estimate value into a data flow. So now I get it. So here I would just I wrote this function to search for the optimized value. result, which should supply the optimized lambda value, which to put together the coefficient estimate evaluated at optimized lambda. Right? And then we throw that aside by lambda argument in the GOM net function. Right? And so we also retrieve the same value with optimized alpha value from the output. And the rest is the same. We have this. We can also give this many coefficient. And we can also see the ROCA used here. But it doesn't seem that during the elastic net improve the receiver operating characteristic means that the proportion of correctly predicted observation from the either the lasso or the ridge regression. But here, just an exercise. So now you know what to do is the lasso feature engineering method on a larger scale. So, do you want further parallel computing for this? I mean, because the reason I want to register for the multiple core in my machine is that, okay, so suppose the data could be very large, right? Just big data, I hate to use this word. So because most of the time you're running only one core in your machine, or even throughout your service line, right? So I would say most commercial electronic is a huge waste to our body because you're not using this maximum capacity. So here's this one core, right? I would say that most likely you should have that dual core. So you're only using one of it most of the time. But here, since I expect that the data processing is a big data, so I want to distribute it equally, the amount of data equally to the core of my machine. For the usable core of my machine, while leaving one spare, because I wanted to do something else. And I want to use that to process this data. Right, so that's essentially what I'm doing here. So here, the parallel computing means that, okay, so I would ask R to redirect the data flow to the 3 core, say, to the n-1 core of my machine. And then for each of the core, I want to apply the set function, or apply the set function at each of the core. So that at time t, at the same time, so your process, let's say, remains simultaneously over the 3 core. So that they should probably economize the times that you can spend for data processing and estimation from. And in your best, if you have a workstation that has a 16 or even 64 core, that will be even faster if you're only running this. Okay, so that's pretty much today's lecture. So if you have additional question regarding your assignment, you can ask me. I can extend the submission by 1 day if you have more question. Also, I will go home and check out the MFX functions. Because that's some problem with the higher order term. Okay? Right. Okay, so let's go back to the lecture. Any question regarding the lesson or today's topic? Good. Or we're still troubling with the penalization. Okay, so